Hi, welcome. My name is Konstantin Weitz, and today I'm going to talk about Backpipe, which is a tool to verify border gateway protocol configurations. So let me start by introducing the border gateway protocol. And I'll do this using an example. So in this example, you see me here sitting in Seattle. And what I'm trying to do is to access a website called iAmsterdam to learn about the wonderful city of Amsterdam. And when I type that address into my browser, kind of magically this website appears, and I can interact with it, and so on and so on. Now the question is though, how does this actually work? How does this website get all the way over the Atlantic, over here to me in Seattle? And to understand this, first understand that the internet isn't just one big network, but instead it's a network made up of smaller networks, each of which is run independently by what we call an Internet Service Provider, or ISP. So, for example, me over here in Seattle, I'm connected to an ISP called Comcast. But other people are connected to other ISPs, like their company or their university. Now, forwarding packets or communicating with people that are connected to just one ISP is fairly easy because the ISP owns all of its hardware. What's more complicated is communicating between ISPs. And this is what the Border Gateway Protocol, or short BGP, is for. ISPs use that protocol to share routing information with one another so they can talk. So for example, the ISP that I'm connected to here will use BGP to tell all of its neighboring ISPs, that's only one here, that it can directly talk to me. And then the ISP that receives that announcement forwards to all of its neighboring ISPs that it can talk to me through that other ISP. And then ISPs that receive that forward that to their ISPs, and they forward to their neighbors, and so on and so on. So eventually, this ISP here connected to Amsterdam will reach the information of how to reach me, and the iAmsterdam server can then use this information to directly send packets to me, communicate with me, and then that website appears in my browser. Great. So far, BGP seems like a pretty standard routing protocol. What makes BGP different, though, is that internet service providers have a lot of freedom in configuring their BGP routers. For example, the ISP here in the middle might decide to implement a policy to never forward announcements to one of its competitors. However, implementing these policies in the actual routers is pretty error-prone. And the reasons are manifold. One of them is that routers are configured in very low-level languages, and it's just hard to do the right thing using those. Then, you're also configuring a distributed system of routers, and all of these routers have to collaborate to achieve the desired policy. And reasoning about that is pretty hard. Finally, there's very little static analysis to help you check whether you made any mistakes. And this has led to real errors in our world. For example, the United States forwarded a large fraction of its internet traffic through China Telecom. And this included military traffic and was thus covered by a congressional report. Second, YouTube went down for several hours due to a misconfiguration in an ISP in Pakistan. And here you can see how brittle the world of BGP is. An internet service provider that misconfigures its routers in Pakistan can break a giant on the internet like Google. Now, to help internet service providers configure their routers correctly, we've developed Backpipe. And Backpipe takes two inputs. First, it takes a specification of the policy that an ISP wants to implement. Second, Backpipe takes an ISP's router configurations. And then it either returns that these configurations correctly implement the given specification, or it returns a counterexample to show a case where the configuration does not correctly implement the spec. Okay, now we know enough to give an overview of the rest of this talk. First, I'm going to give a bit more background on BGP. Then I'm going to explain our specification language. Third, I'm going to show how BACPIPE is able to verify specifications on configurations with hundreds of thousands of lines of code. And finally, I'm going to show an evaluation of BACPIPE on real configs. Let's understand in more detail how an internet service provider implements BGP. To do that, we're going to zoom into the ISP, indicated here by the cloud. And you note that the ISP contains various routers, here indicated by circles, that do the BGP forwarding. And each of these BGP routers contains what we call a routing table. And this routing table stores entries that allow, for example, the router to forward a packet to me over in Seattle. Now, whenever an ISP receives a new route announcement, this is indicated here by the red box, the first thing that the ISP does is import that announcement. And this is where the configurability of BGP comes in. Every BGP router can specify an almost arbitrary function that does the import of an announcement. And that function either maps the announcement to a new announcement. We indicated the change here by the change in color to blue, or it might drop the announcement. Once the announcement is imported, it's stored in the router's routing table. And once stored, it is exported to all of the router's neighbors. Now again, this export filter is very configurable, and it might either change the announcement, or it might drop it altogether. And this process continues on and on and on. Every router on the internet imports route announcements and stores them in the routing table and exports it to all of its neighbors. Now, one last case that we have to consider is what happens when there are multiple announcements for the same destination. So there's two paths through the internet that will eventually reach me in Seattle. And in this case, BGP invokes a fairly complex mechanism to choose one of them. In this case, the yellow one is chosen over the blue one. Great. Now that we understand this background, we can understand how our specification language works. The first part of our specification language are import specifications, indicated here by import question mark. And these import specifications take as input an input-output pair from our import filter, and then either return true if this is a valid input-output pair, or false if it's an invalid one. So for example, for this import filter here to be valid, it must be true that import question mark returns true for red and blue. And these specifications are fairly expressive. For example, we can implement a policy to drop all announcements for localhost. And this makes sense. You can't route packets on the internet for localhost. Localhost is a local thing only. So we express this in our language as follows. We say that the input announcement A, if its destination is localhost, then it must be true that the imported announcement, A prime, is the dropped announcement. However, if the announcement A is not localhost, we return true, which indicates that the import filter can do anything. Now we also have a specification language for export, and this specification language is almost the same as the import specification language. Now we can say formally what it means for these specifications to hold. It means that for all possible network traces T, it must be the case that the import filter returns true on any received announcement and the corresponding imported announcement, and that the export specification returns true for every selected announcement and the corresponding exported announcement. Okay, last but not least, we have selection specifications. And these specify what's supposed to happen when there's multiple announcements for the same destination. And these specifications are written as a ranking of announcements. So for this scenario here to hold with the given specification, it must be true that the specification ranks red announcements over yellow ones and also red announcements over blue ones, because the red announcement is the one that has been selected. And this is generally useful. For example, an ISP may specify that announcements with higher revenue, here indicated by A prime, must always be preferred over announcements A that have less revenue. Now again, we can say formally what it means for these specifications to hold. Namely, for all traces, it must be true that the selected announcements have a higher ranking than all of the received announcements. In summary, our specification language provides three components. It provides import specifications, export specifications, and selection specifications. And what it means for them to hold is indicated by this formula down here. So let me show you what it actually takes to check this formula. So here, we're first going to consider just what it takes to check this formula for one given trace. But we actually have to check for all traces. So the one trace that we're considering here forwards the red announcement, and then concurrently forwards a green announcement and also a blue announcement through an ISP. Now once we have given this trace, it's fairly easy to check that all these specifications hold. All we have to do is check that the import and export of all the announcements that we've had in our trace actually always return true. However, what's hard is that we have to check this for all traces. And there's an infinite set of traces. For example, just consider that after forwarding red, green, and blue, this ISP may also have to forward purple and yellow and whatever other color you can think of, and then maybe withdraw an announcement and send the same one over again. Now our solution to this problem is the initial network reduction. And what this reduction says is basically that instead of checking traces that forward multiple announcements, we only look at traces that forward one announcement at a time independently in the empty network. So for example, what we check here instead is we first check a trace that only forwards red in the empty network, and then we check this formula down here. Then we check green. Again, we forward green in a trace through the empty network, and we again check the formula. And finally, we forward blue in a trace through the empty network, and again we check the formula. And this is great, because now we only have to consider a finite set of traces. And this set is finite because there's only a finite number of paths that announcements can take through an ISP. And there's only a finite set of announcements because the BGP specification restricts how long announcements can be. Now there's one potential problem with this approach. And the problem is that BGP is stateful. So it might not actually be sound to only consider traces that forward announcements in the empty network. Maybe it's important to consider announcements that have been forwarded before and change the state of the BGP routers, because that might influence how announcements are forwarded later on. Now, one of the insights of our paper is that it's actually okay. We can do the initial network reduction. It's sound, even though BGP is stateful. And to understand why, we have to consider the cases where BGP is stateful. The first case is selection. And this is obvious, right? Selection always depends on announcements that I have previously received. However, it is actually impossible for an announcement to be selected only in the non-empty network. And the reason is that when there's no other announcements to compete with the announcement, BGP will always select the only announcement that is actually there. So in other words, if an announcement is ever selected, it is also selected in the empty network because there's no competition. Now the second and final place where BGP is stateful is on export. So whenever BGP exports an announcement, here the blue announcement, and then exports exactly the same announcement again, BGP won't actually send the second announcement. And this makes sense. This allows BGP to save some bandwidth by not sending duplicates over the network. Now the question is, can this statefulness be used to export announcements only in the non-empty network? And again, the answer is no, because in the empty network, there's never been an announcement forwarded before, so it can't be a duplicate. In summary, the initial network reduction is sound because BGP has maximal forwarding behavior in the empty initial network. Now we can use this insight to efficiently implement the backpipe algorithm. So instead of having to check this infinite set of traces, which is impossible, backpipe only has to check a finite set of traces. Unfortunately, though, that set is still too large to just perform simple brute force search. So instead, we need to be a little smart. The first thing that we did is we partitioned this set of traces into small chunks, and then we sent each chunk to a server in a cluster. And so we could parallelize the problem. In fact, using this strategy, backpipe becomes embarrassingly parallel. Unfortunately, even a parallelized backpipe algorithm is not quite efficient enough. So the second thing that we did is represent announcements symbolically and then use an SMT solver to very efficiently check that a specification holds for all symbolic announcements. There's more tricks that we had to play, and these are described in detail in the paper. But let me switch now to the evaluation. We evaluated backpipe on various specifications, including 10 specifications taken from Juniper configuration scenarios, and we evaluated backpipe on hundreds of thousands of lines of code. In the end, backpipe verified that 14 of these policies always hold, and it also found 19 policy violations, in which case the configuration did not correctly implement the specification. Note that backpipe issued no false positives. Now let me describe in more detail one of the case studies that we performed. And this case study was on Internet 2, an ISP with over 100,000 lines of configuration that connects universities throughout the entire United States. Now, we evaluated Internet 2 on 3 specifications. The first one was no Martian. And this specification is similar to the one that I showed you before with localhost. And it turned out that Internet 2 actually correctly implemented the no Martian specification. And it took backpipe 20 minutes to verify this. The second specification that we checked is called block to external. And what block to external does is that whenever an announcement is tagged as private, it ensures that this announcement is never forwarded to any one of the ISP's neighbors. It turns out that this specification does not hold for Internet 2. In fact, there are 5 scenarios in which announcements are leaked to some of the neighbors of Internet 2. Now, it took backpipe 8 hours to verify these counterexamples. Lastly, we check the GAR-Expert specification. This specification roughly says that announcements that generate higher revenue should be preferred over announcements with less revenue. So it took Backpipe 3 days, and it found 14 problems in this specification. Okay, so much for my evaluation. Now let's talk about related work. BGP is very well studied because it's such a crucial protocol used by everyone on the internet. One of the tools was developed by Ryan Beckett, and it provides a high-level BGP configuration language, and programs written in this language are then compiled to the low-level router configurations actually used. Now, second, there's Backfish, which is a tool to verify BGP configurations. However, in contrast to Backpipe, it only checks these configurations for a small set of given traces. Next, there's Netcat, which is again a high-level configuration language, but for software-defined networks. And again, programs written in this language are then compiled to lower-level languages that can actually be executed by a router. Last, there's header space analysis, a tool to verify that routers correctly forward packets through the network. In contrast to Backpipe, the header space analysis tool can only verify protocols that aren't stateful, so it can't verify BGP out of the box. Okay, so in summary, our paper makes the following contributions. First, I talked about the BGP specification language. And I think the insight here is that we treated BGP configurations just like normal programs. And in that way, we could use existing PL techniques like full functional specifications to reason about their correctness. Second, I showed how we were able to scale Backpipe to verify specifications for our configs with hundreds of thousands of lines of code. And the insights here were the initial network reduction, then parallelization, and finally, symbolic execution. And I want to note here that symbolic execution worked very well because we're in the domain of networking, where configurations are fairly simple programs. They usually don't have any loops or many chunks, and so it's very easy to check them using an SMT solver. Lastly, we performed an evaluation of Backpipe on real configurations, and we were both able to verify that configurations are free of certain kinds of bugs, and we were able to find violations where they actually did not correctly implement the specification. If you want to know more about our tool, you can go to backpipe.udoptools.org. Thank you very much.